Okay. Very good morning to all of you. We are live now, and we will be going through this. But I guess there is some issue, is there? Yeah. Hello. So, not many are there right now. Never mind. We will begin with this and we will complete this. Those who join in, they will enjoy the part. So, let us begin. Just we'll hold on for a few minutes and then we will begin with the whole part. Um, like if anybody is joining in. Yeah. Okay. So we are beginning with the main portion of diagonalization and checking whether a matrix is diagonalizable or not. So how do we do? We have already seen that whether a matrix is diagonalizable or not in our last session of live. Now we will see how to check or how to show whether a matrix is non-diagonalizable, or what happens when the case that the matrix is non-diagonalizable, how to handle it. Okay, so let us see some questions related to that, and it will boost our confidence on diagonalization, because diagonalization has great importance in mathematics as well as in computer sciences and other uh, places where image processing and further concepts are involved, and especially image processing and some related to market research also. So let us begin with that now. uh, yeah, so we take up the following question today, is that to check whether the given matrix is or not. I'm sorry. Okay, now how do we do this? Now the first thing over here, we will take this matrix. Let's say A is equals to, we take up matrix 2 2 3 4 minus 1 1 0 0 and 0. This is the matrix we take up, and we have to check the same thing for the matrix. So how do we start? First we have let Ax is equals to lambda x, x is not equals to 0, and then we check here how to go about it. So here we will now go and find the characteristic equation, but in this kind of a matrix it's very straightforward. Okay, so it is determinant A minus lambda I equals to 0. The matrix is triangular matrix, so when you take determinant, it is going to be 2 minus lambda, 2 minus lambda, 1 minus lambda, 3, 4 and minus 1, and 0, 0 and 0. This is equals to 0. So now when we try to find the determinant, now since it is a triangular matrix, determinant is nothing but the diagonal element product. So your answer is 2 minus lambda, 2 minus lambda, 1 minus lambda equals to 0. This is the answer for the determinant. Now the next part is we have to find the eigenvalues. So eigenvalues are pretty much available. Lambda 1 is 1 and lambda 2 is 2 comma 2. Okay, there are two eigenvalues. So here we can say here am of lambda 1 is 1. That means it is the algebraic multiplicity of lambda 1 is 1. Okay, now then we can also add am lambda 1 is 1, but we'll write like this otherwise here, and is 1, and am of lambda 2 equal to 2 is 2, like this. Okay, so we write like this way and we get the answer for am of both of the eigenvalues. So now let us see. Firstly we will check directly. See, if we go for lambda 1, it will be just a waste of time because it is having algebraic multiplicity 1, so the chances of it being having an eigenvector is also very high. So we will first check for lambda 2. So we will check for lambda 2. For lambda 2 equal to 2, a minus lambda 2I operated on multiplied by capital X equals to 0. What do we get here is 0, 3, 4. Here you get 0, here you get 0, here you get minus 1, right? And then here you get 0, here you get 0, and here you get 0. Okay, and then there is this x1, x2, x3, right? This is what we get. So which is equals to 0, 0 and 0. So from this system we get the what we call few equations. What are the equations we get? We get 3x1 is equals to we'll get 3x2 is equals to 4x3, and we will get minus of x3 is equals to 0. Okay, so here what we get is this 3x2 is equals to 4x3, and then we get here is minus of x3 is equals to 0. Now what does this mean? Minus of x3 equals to 0, it means that x3 is 0, right? And we have again we got a relationship that 3x2 is equals to 4x3, which further implies that 3x2 into 4 is equals to 4 times 0, which is 0. Therefore x2 is also 0. We get two straightforward answers here, that x3 is 0 and x2 is 0. Now, so what about x1? X1 becomes free. How do we come to know that? We can check from the rank part also. So here n is equals to 3, rank r for a minus lambda 2I, which is rank of a minus 2I. This is become 2. We can check this. The rank over here is 2. So therefore n is equals to, therefore if we try to calculate the geometric multiplicity, which is n minus r, that is 3 minus 2, that has become 1. So here it is very much clear. Okay, so here it is clear that am of lambda 2 is 2 and gm of lambda 2, which is 2, is 1. Okay, hence we can say that matrix A is not diagonalizable. Okay, this is what we get. So please go through this example and you can realize it, how it is working. Okay, so we will see now how does this work. I'm just checking some settings whether they are going correct or not. Okay, so now let us see how to go further. Now this kind of matrix is not diagonalizable, so this is here the conclusion comes that the matrix is not diagonalizable. So here again one very important note I want to make and give it to you, that is let us see here. The note is, I give you this in yellow. So the note is that if a n cross n is an triangular matrix, then its eigenvalues are its diagonal entries. Okay, this is the one. So that's how it is. Yeah. So now we are here. So a very good morning. Uh, yeah. So I hope you have followed this. I was not able to see any one of you there on the chat, so I was slightly dubious about it. But no, never mind. So this is one of the result. Then the eigenvalues are its diagonal entries. We would see them again. But since the question came up, I told you how to get it done. So now let us see another kind of example. Sorry. um, how to handle this. Now let's take up another example here. Let's say we have question is here that check whether the matrix is diagonalizable or not. Now if this is the case, how do we handle it? So the matrix is again uh, like similar to the previous one, but a different 2 to 1, minus 1 to 2, and 1 minus 1 minus 1. Okay, now this is not triangular, but now let us see how to handle this. Again we write the most standard steps. Let ax is equals to lambda x, okay, such that x is not equal to 0. Then determinant a minus lambda I is equals to 0. So determinant of we subtract from diagonal, subtract lambda, so 2 minus lambda minus 1 minus lambda, and here up minus 1, here there minus 1 1, here 2 1 and 2. Okay, that's what we get. And now let us see how to handle this. So we find the characteristic equation. So the characteristic equation will be how much? Lambda cube minus trace a plus trace a times lambda square. Okay, trace a times lambda square plus m11 plus m22 plus m33 lambda okay, and minus determinant of a equal to 0. So this is the formula. Therefore lambda cube minus, when you do the trace, it is 4 minus 1. Okay, so 4 minus 1 will be 3 here, so 3 lambda square. Now let us calculate m11. M11 is delete the first row first column, so you have m11 is 0. M22 delete second row and second column. Okay, so it is 2 into minus 1, minus 1 is 3, minus 2 into minus 1 is minus 2, and then there is minus 1, so it is minus of 3. Okay, M33 when you calculate, you have you delete the third row and the third column, so you have 4 and minus 2, so 4 and minus 2, minus 2 and 4 and minus of minus 2, so you get 6 over here lambda, and the determinant of this is going to be 1, I guess. Just calculate the determinant. If you are doing any determinant calculation, let me know what is the calculation you get over here. So the determinant is going to be 1, I believe. So just check. Are you getting determinant 1? Let me know in the comment section that the determinant is 1 or not. By the time I'll also calculate here. So I am sure the determinant is 1. So let us see here, it is going to be 1 equal to 0, and then it is, therefore we have lambda cube minus 3 lambda square plus 3 lambda minus 1 equals to 0. Now if you see this, you can solve this thing in your calculator. You will get lambda equal to 1, and basically this is nothing but your lambda minus 1 the whole cube equals to 0. So you will get lambda equal to 1 1 1 repeated 3 times. So we immediately write down over here that am of lambda 1 equal to 1 is 3. Okay, algebraic multiplicity is 3. There's nothing fancy over, but it is, for the first time you get 3, right? Now we go for calculating the eigenvector. So let us see, do we get 3 different eigenvectors from the one single situation? Possibly the answer is no. So let us see. So now we write here, now to find eigenvector a minus 1 or lambda 1 I into capital X equals to 0, therefore a minus I into capital X is equals to 0, This gives you 1, yeah, so 1 minus 1 1, right? After that you will get the matrix is 2, right? Here it is 2, then there is 1, here it is minus 1, then here it is 1, here it is 2, and minus 1 and minus 1 is minus of 2. Okay, so now let us see how to handle this. What we can do is x1 x2 x3, that is equals to 0, and you take, okay, you will get here, uh, here you will get, you will need to change using row transformations, and I can see some kind of similarity is there between the first and the second and the third row, right? So yeah, we will try to manage that, but now we do the row transformation. So r2 changing to r2 minus r 2r1, okay, r2 changing to r2 minus 2r1. When we do, we get here 1 minus 1 and 1, and then this becomes 0, this one will become 1 minus 1 is 2, and here this becomes minus 2, and here the third row you can do r3 changing to r3 minus, oh, just a minute, I think I made a mistake here. It is not 3, it is not 2, here you must get 3, yeah, 1 minus 1 will give you 3, 1 minus of minus 2, right, it is, see, basically it is 1 minus 2 into minus 1, here you will get 1 plus 2, so that is 3, and then there is minus 1, then minus 2 into 1, so you get minus of 3, yeah, minus of 3 is here. And then when you do the following subtraction, that is r3 changing to r3 minus r1, you will get 1 minus 1 is 0, here you get, again you will get 3, and here you will get minus 2 minus of 1, it is 3. Okay, so x1 x2 x3 is equals to 0. So this is what you get. Are you getting that? Yeah, let me know in the comment or the chat section that you are able to do that. Now yeah, so what do we do here? The next one is this, from this one, from we perform the following thing. We can perform now r3, right, here there is minus sign, so r3 changing to r3 minus, we can do r3 minus r2. When we perform, we get 1 minus 1 and 1, and here it is 0, 3 minus 3, 0 0 0. So x1 x2 x3, this is what we will get. Now we have here 0 0 and 0, so here we see that n is equals to n, which is the number of unknowns, which is equals to 3, rank r, which is rank of a minus I. Okay, I'll just erase this a bit. A minus I is going to be 2, and therefore gm of lambda 1 equal to 1 is n minus r, which is equal to 3 minus 2, that is 1. So we can now conclude that here am of lambda 1 equal to 1 is 3, which is not equal to, we can write like this, which is not equal to gm of lambda 1 equal to 1, which is 1. Okay, therefore matrix capital A is not diagonalizable. This is what it is. Okay, so here we get the following matrix, and this is how we are supposed to do the question. So these are the two examples that were crucial from my point of view in discussing regarding the what we call the important questions regarding diagonalization and all. So be very careful while doing the questions, because we need to be very cautious about how the questions are going to come across. All the questions, some questions sometimes they ask these kind of questions also, that find whether the matrix is you know find the eigenvalues and eigenvectors. That's it. They don't even check at the end whether the matrix has a good eigenvalue or not, but sometimes they happen to be very tricky and dangerous. So be very careful while doing these kind of questions. I'll just check on the other end that like if anyone if you have any doubt right now, you can put your doubt in the chat. I'll try to solve it as much as possible, and we will see how to get it done. If you have any doubt in your exam, then you can ask me, or like in your exam, I mean to say in your previous exam questions, if you have seen any, then you can ask me, and otherwise we can continue with the discussion of our questions that we have taken up. Okay, I believe there are no doubts right now. I'm sorry. Now we will take up some very important questions regarding properties, and which are always there in the exam. So these are the properties of eigenvalues which are very important. These of eigenvalues, and these questions are always asked in exam. Yeah. Oh, good morning. Um, Thank you, Akash. Now we continue that these are always there, and these questions generally come for 5 marks in examination. But now see, what you can do is 5 marks or 6 marks, okay? 5 and 6, 8 they never come. So what is important regarding this kind of questions, you need to remember the table kind of thing you can make, or you can remember the statement. I'll take up here. uh, they are generally given in this way, okay? But sometimes we also need to remember the eigenvector also. So first we'll note down what happens with eigenvalue. So if we first generalize, if a n cross n is a matrix, with lambda 1, lambda 2 up to lambda n as eigenvalues, then the first result comes here. Eigenvalues of a to the power k are lambda 1 to the power k, lambda 2 to the power k, so on up to lambda n to the power k. This is the thing, okay? Then what are the eigenvalues of see, eigenvalues can be they can be complex numbers also, but then we are not dealing with complex numbers because they generally don't come in exam. They can be there in MCQ question, they can be there in competitive examinations, but they are not asked most of the time in examinations regarding complex eigenvalues, okay? But we'll still see how to handle them. B, then eigenvalues of A transpose, okay? A transpose are lambda 1, lambda 2, lambda n. No change for transpose. Then eigenvalues of A inverse are 1 upon lambda 1, 1 upon lambda 2 up to 1 upon lambda n. Third, eigenvalues of adjoint of A, okay? Adjoint of A are determinant of A, so they are generally written like the determinant A over lambda 1, determinant A over lambda 2, and so on up to determinant A over lambda n. This is how they are given, okay? So these are some important properties. Now we'll again, there are more are there, we will see them. So we A, B, C, D we saw. Now we will see some another property now. Then there is this. that the next thing is, if if determinant of A is 0, if determinant of A is 0, then at least one eigenvalue is 0. This is very important. Okay, then another thing is there. hmm. Then if A is Hermitian, Hermi, Hermitian, then the eigen values of A are real numbers. Okay, that is how it works. This is very important. Then we go for skew Hermitian. So if A is a skew Hermitian, matrix, then the eigenvalues of A are either purely imaginary or 0. This is how they are. Okay, now from all these, because of Hermitian and skew Hermitian, now we can write about something. These are very important, E, F, G, H. Now we'll go for another important one, that the if A is a real symmetric matrix, then its eigenvalues are real numbers, are real numbers. Now there is one more result over here. Correspondingly also, if the eigenvalues of A which is real symmetric, okay, real symmetric matrix are real and distinct, then the eigenvectors, okay, eigenvectors are mutually orthogonal, orthogonal, okay. What does it mean? It means that their dot product is going to be 0. We will see that kind of question when it comes. Right now we will just make a note of this, because this is how all things have come up, okay. Then we go for the next important result, that is, if A is a skew, if A is a skew Hermitian matrix, then eigenvalues are either, I think we wrote regarding this skew Hermitian matrix, either yeah, we have written this. Then you can write down skew symmetric, we can take skew symmetric matrix, then the eigenvalues skew symmetric matrix, but then skew real symmetric, okay, skew real symmetric matrix, then the eigenvalues are either purely imaginary or 0. And yeah, then we will there are more properties are there, but then I'll just give you this one last property which is very important, maybe two more. Yeah, if A is n cross n matrix with eigenvalue lambda 1, lambda 2 up to lambda n, then k times A n cross n has eigenvalues, you can call this as sub 0.1 in this, k times A has eigenvalues k lambda 1, k lambda 2 up to k lambda n. Second point here is, if this is what we have, then okay, then there one more thing here, that is that A plus ki has eigenvalues, which is, this is also n cross n, okay, has eigenvalues lambda 1 plus k, lambda 2 plus k, dot 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 lambda n plus k. Now these are more than sufficient properties according to me, and if we say like this way, you can just have this maximum. I can give you this one kind of a different example, that is, if we have a raised to k plus m into a raised to k and a raised to some say p, doesn't matter, okay, some power, then eigen has plus or minus, okay, doesn't matter, then a has, this is all n cross n, a has eigenvalues lambda 1, okay, you have to add corresponding eigenvalues, a raised to lambda 1 raised to k plus minus m lambda 1 whole raised to p, then lambda 2 raised to k plus minus m into lambda 2 whole raised to p dot 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 lambda n whole raised to k plus minus m into lambda n whole raised to p. Okay, this is how it will look like. We will see this example. Now there are too many properties about them, still properties are pending. We won't go into so much of detail because they are always there, you know, these properties won't end, because as and when idempotent, nilpotent and more matrix if you pour in, these properties go on increasing. These are, which I have given you in these 3 slides, these are the fundamental or the basics, basic versions of the property which are there regarding eigenvalues. If you remember these many, I think it is more than enough. Okay, and then they don't ask too much about other stuff. You can even find out later on regarding them. Okay, I'll just let us take up an example to have a gist of what happens when the properties are dealt with. So let us take up now. We take up the example, and these are popular examples. Find the eigenvalue of property questions. These are very popular questions which are asked in exam most of the time, and you can do it sometimes orally, you can get the answer, sometimes it is very straightforward. Find the eigenvalues of matrix a cube plus 3a square minus 2i if a is equals to I'm taking any random question from my mind, 2 3 1 and 0 5 6 0 0 0. Now for this they have asked us to find the eigenvalues. So what you can do, firstly you use the first result. You can write here lambda ax and all that, not a problem, but here you can straightforward write, we are not finding eigenvectors, we are just finding eigenvalues, so we need not write that lambda a x equals to, for this you can jump that step, but here you can straight write, or if you even write, not a big problem. If you feel comfortable, let's write Ax is equals to lambda x is not equals to 0, therefore determinant a minus lambda I is equals to 0. Fine. Here we mention here capital A is upper triangular matrix, hence eigenvalues are its diagonal entries. Okay, eigenvalues are its diagonal entries. Now therefore lambda 1 is equals to 2, lambda 2 is equals to 3, and lambda 1 is equal lambda uh, 3 is 1. Okay, now we are asked, so we write like this way. You can make table, or you can make, uh, write the thing properly, that's it, nothing more comes on this part. So eigenvalues, we'll just write the I'm making a table, matrix and the eigenvalues. So what you need to do is, do not change the order of eigenvalues in between the answer. That's the word of caution, like yesterday we had seen. So caution is, in between, do not change the order of writing the eigenvalues. Okay, that would give you very dangerous answers. Okay, please remember this. This is very important. Do not change the order in which the eigenvalues appear. So here the eigenvalues are matrix. For A we have eigenvalues lambda 1 equal to 2, lambda 2 equal to 3, lambda 3 equal to 1. So eigenvalues for A square will be lambda 1 square, which is 4, lambda 2 square, which is 9, lambda 3 square, which is 1. Now A cube is lambda 1 cube is 64, or we first write here, even if before going to that A cube, we will first find eigenvalue for a raised to 3a square we will find. Okay, 3a square eigenvalues are going to be, here they are going to be 3, it is stuck up now. Let us write still. So lambda here is going to be 3 into 4, so it is 12. Then it will be, we multiply 3 to 9, okay, so 3 and 9 will give you 27. Here it gives you 3. What about a cube? A cube lambda will be, a cube you will have 2 cube, so 2 cube is 8, yeah, and here 3 cube is again 27, and 1 cube is 1 cube is 1. And therefore for I you can write here I, here you have 1 1 1, and then you can do the table in the next part. I'll take up the table here. So I'll just write the table again. Mhm. Yeah, so the table here is, matrix is here, eigenvalues, so you have A is lambda 1, lambda 1 was what happened, just a minute. System, so here lambda 1 is lambda 1 is 2, lambda 2 is 3, lambda 1, lambda 3 is 1. So for a square you had 4 9 and 1. For 3a square you will have 3 into 4 is 12, then 3 into 9 is 27, then here you will have 3. Then next here for a cube you will have 2 cube, 2 cube is 8, then here you have 27, and here you have 1. Then for I, eigenvalues are 1 1 1, then for 2I you will have 2 2 and 2. So finally the eigenvalues what we want are a cube a cube plus 2a square, right, or 3a square minus 2i. When you want this way, so you do 8. What you do is 8 minus 3a square. 3a square eigenvalues are 12. Okay, 12, and then here minus 2i, so that eigenvalues are minus 2 here. And then again over here a cube is 27 minus 3a square. 3a sorry, a cube is 3a square minus 3 sorry a cube is 27, and 3a square you add, just a minute, we have to add over here a cube. See, a cube eigenvalue is 8, and then you have plus 3a square, plus 3a square is 12. Okay, so you add that, and for eigenvalue for a, which is 2i, you subtract 2i, 2. So here it is now 27 plus 27 minus 2. What will happen here now for a cube? Again, for the third section eigenvalue is 1 for a cube. For 3a square eigenvalue is 3, you add it, minus 2i, so minus 2i is minus 2. So final eigenvalue answer are going to be 20 minus 2, 18. Here it is 27, 27, 54. 54 minus 2 is 52, and 1 plus 3 is 4. 4 minus 2 is 2. So therefore we write here, therefore eigenvalues again some fuss. So eigenvalues here, eigenvalues of a cube I guess some RAM issues. A cube plus 3a square minus 2i are 18, 52 and 2. Okay, I'm sorry, I hope you followed this, because there was some glitch over there. I'll take one more example for clarity so that we understand how to handle these. Okay, because these are the kind of questions that will come in exam also. They are very popular, and many of the times children write in a wrong way and they land up into wrong answers. So once you are done with this, let me know. We will see another kind of example on this, and we will do some other examples. Now, uh, let me know once you are done. So we now take a new question here. This is one of the questions which was asked in one of the examinations of MU. So let us see that. Find the eigenvalues of A equal to -1, 3, -2, 0, 0, 0, 2, 5 and 3. This was one of the question. Yeah, thank you. uh, Thank you. uh, I think see there is this time speed is different. So my video is running a bit late, maybe 2 minutes, I think, maybe 2 or 30 seconds late. So uh, I'm a bit ahead in this, and I see the comments a bit late. So never mind. So find the eigenvalues of this, and also find eigenvalues of a cube plus 5a plus 8i plus a inverse. Okay, now I'm sorry. So here we go ahead with this, how to handle this again. So again we write here answer that let uh, let lambda be the eigenvalue. You can write like this: let lambda be the eigenvalue of a. Now since a is upper triangular, its eigenvalues are its diagonal entries. Therefore lambda 1 is -1, lambda 2 is 3, and lambda 3 is -2. This is what we have to do. Now we make the table. Okay, so making the table, I'll make it on a fresh page so that calculations I can show. So here it is, matrix A, eigenvalues. Okay, so the eigenvalues here are lambda 1 equal to -1, lambda 2 equal to 3, and lambda lambda 3 equal to -2. So a cube, first we find for a cube, doesn't matter, or you can find any one whichever you like. So let's find for a cube first. So a cube eigenvalues are lambda 1 cube, which is -1, lambda 2 cube, which is 27, then lambda 3 cube here, which is -8. Okay, this is what is the answer for a cube. For phi a you will have here 8 times 5, so 5 times lambda 1, which is -5. Here then you have 5 times lambda 2, which is 15, then 5 times lambda 3, which is going to be -10. These are the eigenvalues for phi a. For I, you have eigenvalue as 1, 1 and 1. So 8i eigenvalues are 8, 8 and 8. A inverse eigenvalues are 1 upon, right? So we had seen in the property A inverse eigenvalues are going to be 1 upon. So it is 1 upon lambda 1, so that is -1. 1 upon lambda 2, which is 1 upon 3. Then 1 upon lambda sorry, lambda 3 is -1 upon 2. So what do we get here is, therefore, eigenvalues of a cube plus phi a plus 8i plus a inverse are, what are they? Let us just add them up and we get our answer. So on adding we will get what all things we will have to add. Therefore our answer will be a cube. A cube is -1 plus phi a, which is minus of phi, and then 8 is 8, 8i is 8, and then here it is -1. Okay, we will solve this, but we'll add first. Okay, so here it is, a cube is 27, and then there is phi a is 15, and then there is 8, and then there is 1 by 3. Here there is here we have is a cube is -8, then we have phi a is minus of 10, then there is 8i is 8. Okay, and then there is minus of half. So here the final answer is going to be, see, -1 -5 and -1 again here. So this is basically 8 minus 7, so that is 8 minus 7 is 1. Here you will have 27 plus 15 plus 8, plus 8 plus 1 by 3. So you get your answer, yeah, plus 1 by 3, you get 151 by 3. Don't get scared by any fraction. Okay, doesn't matter, that number can be anything, it is just there. Okay, and then here it is -10 minus half, that is -21 by 2. I hope you followed this. Did you follow? Let me know. Number can be anything, okay? You don't have to get scared of the numbers. I'll just write this thing properly because it appears to me like a mod sign. So I'll just write this here as um, 7 plus 15 plus 8, yeah, sorry, 151 divided by 3. So yeah, thank you that you have followed this, and this is all about eigenvalue and eigenvector, eigenvalue and eigenvector for related to its property. This is how you solve the question. There are other ways are also there. You can write uh, all words and words, but I think this is the table is self-explanatory. Yeah, when you make the table in exam, leave one line, one or two lines, so that you know the fractions and everything is calculated properly. Do show your calculations, don't write wrong notations, that is very important, and that would fetch you the maximum marks. Okay, this is on this. Now I want to tell you one more important concept. There is something called as powers of matrices, power of matrix A. So powers of A. Now powers of A, or even sometimes you can call it this as a function of A. uh, a function of A is a more general version, but let me first tell you. Now see, let A be a diagonalizable diagonalizable matrix. Therefore we have A is equals to P P D P inverse, where P is non-singular, and D is diagonal matrix. Okay, yeah, we know that it is made out of um, the eigenvalues and eigenvector, but essentially this is the format. Okay, now see, how do we come to know this part? This part is A raised to, like, suppose if now see, when computers advanced, okay, when they need lot of mathematics, you just can't say that software will calculate. Software also needs some input, right? It will not go on its own. Initially it wasn't possible, so everything, all these mathematical things and terminologies, when they started getting meaning into the world of computers, so there is obviously a great need to calculate powers of a particular matrix, because as then when complexity develops, we have to check every other stuff also. So now one of the theoretical aspect is this, like this. Suppose if I do a square, simple, I'll give you an example. A square for me is a into a, but then approach can be like this also, that though it is a into a, I can write this as p d p inverse multiplied by p d p inverse. This is how it can be done. Now I hope you are following this. Okay, so this PDP inverse can be now seen as P D P inverse P D P inverse. Now if I take these two in one bracket, what do I get is identity here. P inverse P is identity, so I get P D I D P inverse. Okay, so this is P D D P inverse, which is essentially P D square P inverse, right? So therefore what I concluded here is a raised to 2, okay, or a square of a matrix is P D square P inverse. This is what I got. Similarly, I can do for a raised to 3 also. So a raised to 3 will be, a raised to 3 will be p d raised to 3 p inverse. Okay, so then they can ask you what will be a raised to, what will be a raised to k. So our natural answer which we come to know is a raised to k will be p d raised to k p inverse, right? That is what it is going to be. So this is very common thing that you come across. Okay, so this is um, one thing. Now here you have to remember that, see, squaring a matrix, see why this is very important. You will come to know now. Squaring the matrix is a very difficult task. Okay, you know, you need to perform that row column operations properly, and compatibility and etc. we have to check all the time. But this thing runs faster in computer. The reason is, if I get that matrix A becomes diagonalizable, I have to calculate P and P inverse. That's it. Okay, that can be done very quickly. And A cube, maybe it's not that difficult, but if I tell you find a raised to 75, a to the power 2000 or something larger number, then my, in computer, if computer works like that, a into a into a into a 2000 times, it will take a decade, right? Now you, to fetch that much of data, and so much of things will go into it. But then a raised to k, if you have this algorithm, p a raised to k is p d raised to k p inverse, then computer can directly get d to the power k, and then you can get this answer. Okay, so but now what is d to the power k? So if d is a diagonal matrix, diagonal matrix, in our case it is lambda 1 lambda 2 up to lambda n, right, dot dot, and here there are 0, then d raised to k is nothing but lambda 1 raised to k lambda 2 raised to k dot dot lambda n raised to k, and this. Okay, so this is regarding powers of the matrix. So you can handle this small questions. So let us see here a small question here, that if let me take a very small question so that you get familiarity regarding the whole concept. Yeah, suppose if a is 1 minus 1 0 and 2. Okay, if a is this, find, in exam you can get this kind of questions also, find a raised to 35 or a raised to 10, nothing, no problem, or find a raised to 10, let's say a raised to 10 you have to find. And they can also ask you find a general formula for a to the power k. This kind of question can come. So what do? Is we first find the eigenvalues. So answer, here a x is equal to lambda x not equal to 0. I am now writing it here straight away that lambda 1 is 1 and lambda 2 is 2. Reason, what is the reason? Since a capital A is lower triangular. Okay, if you have not followed, let me know regarding this, because this kind of question can come in exam also, or final exam. Okay, so if this is there, this is not that difficult, it's very easy. You just have to remember that this is a trick to see. But what application I told you in computers, it is very important that you need to calculate. Otherwise, why these general formulas? Why to even complicate your brain so much that all these power k? And the moment, what fascinates me in mathematics, the moment you put k equal to 1 and 2, you get some special version. 1 2 3 small numbers, when you put, you will get some special cases. But when you put a number very large, let's say you put 2000, 7000, 9000, that is the time that number will magnify. And that is the place where you need algorithms coming into picture. You rather not algorithms, but you need some devices to calculate. Otherwise, you need to be very intuitive and intellectual to calculate so many higher powers, or you need some technique, or you need to train your mind to calculate that, maybe Vedic mathematics or something. But the numbers would turn large pretty fast because of the multiplication and the power. So this is another important thing that I wanted to tell you, that these things are crucial from the computational point of view, or computer mathematics. Okay, now since A is upper triangle, sorry, A is a lower triangular matrix, we have lambda 1, lambda 2 as the eigenvalue. Now for lambda 1, we calculate A minus I times x equals to 0. So what do we do is 1 minus 1 is 0, 0 here 1 and minus 1. Okay, x1 x2 equals to 0 0. Okay, now when we calculate here, we get minus of x1 plus x2 is equals to 0. So x1 is x2, capital X is the formula, x1 is equals to x2. So x2 x2 both. So you have x2 outside. Your first eigenvector is 1 1. Put x2 equal to 1. So capital X1 is 1 1. Now we go for calculating for lambda 2 equal to 2. You have a minus 2I times capital X equals to 0. Then you have here 1 minus 1 0, and here it is minus 1 and 0, right? So this is x1 x2 0 and 0. So next here when you do the multiplication, so what you get, there is only one value here, right? That one value here is minus of x1 equals to 0, and basically it is just one equation in front of us. So it implies x1 is essentially 0, and second variable we have no information, therefore x2 is free. So I have my capital X as x1 x2 x2. Okay, here it is x1 is 0, x2 is x2, no change for x2. So x2 coming here, it is 0 and 1. Now what do? We do put x2 equal to 1, and therefore we have here uh, your capital X2, which is 0 1, right? And hence we now go for the next part. Therefore P, which is there, which is made up of x1 x2, we calculate that. So that matrix is going to be, our P is 1 1, okay, and this is 0 1. This is our matrix P. And now if we calculate our P inverse is basically 1 1 minus 1 and 0. So now we and D matrix is going to be 1 and 2 0 0. So P inverse, which is A, okay, since A is diagonalizable, we will have here therefore P, or we can write like this, it would be better. This would be nicer thing would be A is equals to P inverse. Therefore A raised to 10 is PD raised to 10 P inverse. So A raised to 10 when we calculate is going to be P is 1 1 0 1, D is going to be 1 raised to 10 0, 2 raised to 10 0, and P inverse is 1 minus 1 0 1. Okay, 2 raised to 10 is, I guess, 1024. Yeah, 1024 is 2 raised to 10. Yeah, so you multiply them. The moment you multiply them, you get 1 1 0 1 here, and here it is 1 0 0. I'll just write this and then multiply, and here minus no, not minus 1, minus 1 0 1. Now you perform the multiplication. Can you guys perform the multiplication, those who are online? Oh yeah, like the video is still behind running, or it hasn't reached the peak, maybe. Has it? Those of you are online, can you calculate on your you know, can you calculate and let me know how much is it? Calculate the answer. So you must get something here. A raised to 10 is 1 minus 1023 01024. This is your answer. You must get this. Try to check your answer with the answer that I'm giving you, because I'm doing it quite quickly, and maybe you might find it, how did it happen. Yeah, so just put your answer in the comment section, or if it matches, just let me know that yes, it has matched, answer has matched, and so you get the answer. Let me know in the comment section that the answer has matched. Yeah. 1 0 for the first one, yeah, minus 1 0 2 3, and yeah, that's the answer. So I hope you got this. Now there was one more question that was asked there, and find a general formula for a raised to k, right? So now general formula, let us write down the general formula. So for general formula, let us do this. What you need to do is you write a raised to k is equals to, therefore a raised to k is p d raised to k p inverse. So here you write p, that is our p is 1, yeah, 1 1 0 1, and then it is 1 raised to k 0 0 2 raised to k, and the inverse we had is 1 minus 1 0 1. Okay, so we need to multiply this and we see what do we get. So here it is 1 1 0 1. 1 raised to k is always 1, so um yeah, that is always going to remain that. So I'll just write here, and here you have 1 minus 1 0 1. This gives us oh no, Akash, you have to check your answer. It has to be this. Have you done any calculation error? Just check, because this is the answer. This answer, it's different for you. You have to get your answer corrected. It must match this answer. Have you done the multiplication correctly? Or just check your feed in the calculator. Have you given the proper input in the calculator? This is what we have to do in the calculator correct way, then you get the answer. Okay, so just check your answer once more, and otherwise this general formula should be able to give you the correct answer. So a raised to k, you do the multiplication, so 1, that is what we get, and then here we get 0, here it is 1, and then here you get 2 raised to k, then here it is 1 minus 1 0 and 1, right? So here it is 1, then there is 0, here it is yeah, 1 0 1. No, 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 it won't come. There is some mistake. The first line, see, when you do the multiplication, yeah, how, what, 2 raised to k, 2 raised to k, 2 times 2 raised to k, no, 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 something is wrong there. First, here it is this, okay, that is an identity, that is correct. So here you will get 1 minus 2 raised to k, yeah, and in the second one 2 raised to k, yeah, that is what you were saying. Okay, fine, yeah, correct. So uh, uh, here we have got the answer from Akash. Yeah, Vivek has given the answer, and Akash, you can verify your answer from this general formula also. See the general formula, the moment you put 10, k equal to 10, you must get 1 minus 2 raised to 10, right? So there is some mistake in the calculation you have done. Please check your calculation once more and you will be able to get the answer. The general formula, when you have multiplied, we get this answer. So this is the answer. Okay, this is how you get it done. Now let us see how to handle for the same question. We will extend this question again a bit more, just a small extension, and then we will stop. This is the last part that I wanted to deal on this eigenvalues, that how to handle sub function of a matrix. Okay, function of uh, the matrix. Now see, I am dealing with this for distinct eigenvalue case. For repeated there is slight differences there, but then we can see it some another time, not now, because I don't want to stretch the lecture too much. So function of matrix, and we will see distinct eigenvalue case. Okay, distinct eigenvalues case. So when you have this, um, what you do is, if you are asked a if a is diagonalizable, is diagonalizable matrix, then a is PD P inverse, right? Okay, now if a is equal to PD P inverse, and let f of a be a function of matrix. It could be anything. It could be a polynomial, it could be uh, anything. So what you do here is, f of a is equals to, again it is p f of d P inverse. Okay, this is the general way of talking about the function over here. So suppose you are asked, now see, what did we see right now? Also we saw that a raised to k is a function of a, right? So same way there can be some questions can be like, find, like you can get in exam, find e to the power a, or say cosine of a. Now cosine of a matrix and e power a matrix, you have never seen how a matrix goes in the power and what does it give, right? We never write a matrix in a power notation, but there is a concept for matrix also, that e a matrix can also go in power. There is nothing stopping in mathematics anyone. So what do you do for e raised to a? So we write here, we take for the same question, okay, find e raised to a and cos a for same question. Okay, we'll do this. Now this is very easy and not at all a difficult task. So what do you do is, we write, let a let f of a equal to e to the power a. Okay, therefore f of d is e to the power d. Now what is e to the power d? We don't know e to the power a. We cannot find e to the power a directly, but e to the power d can be found directly. That is, you just have to raise the eigenvalues by power e. So it is e raised to 1 and this is e square. Okay, so like if you have I'll give you a note over here, then it would be better for you people to understand that what is f of d. Like f of d is f of lambda 1, f of lambda 2, dot dot dot, f of lambda n. Rest other places you have your matrix as the way it is, only the diagonal is affected. Okay, so now if I want to find e to the power a, so e to the power a is here. So f of a is p f of d p inverse we do. So p is 1101 and f of d is e 0 e square and p inverse is 1 minus 101. Okay, so we do the multiplication, you get e, then e square, no, not e square, sorry, um, you will get here, this is first one, this is second, so you get 0, here it is e, and here again it is, here it is e square, then 1 minus 1 0 1, and then here you get e, yeah, and then there is e raised to, here it is 0, here you get e minus e square, and in the last one you get e square. So this is function a, f of a. That means therefore you have e to the power a defined as e minus e square, 0 and e square. This is the value for the function e raised to a. See how mathematics enables you to get this. Now let me tell you what is e to the power a called in the world of mathematics. This is just for the knowledge purpose. E raised to a is called matrix exponential. You must be familiar because these things are used very much everywhere. Matrix exponential, if you don't know, then it is like an injustice happening. When the concept gets introduced, these terminologies must get introduced, otherwise there is no point in learning them. So these are called matrix exponential, and they are useful in differential equations. Okay, when you study system of differential equations, that is the time. See, now everything is connected. That's why, but I'm not going to go there right now. I am just giving you the name and where they are used. Okay, now what was there? Cos a. Yeah, cos a is also something similar. So for cos, now the case 2, let f of a equal to cos of a. So f of d is equals to, you will have cosine of d. Cosine of d is cosine 1. Don't write any degree or any numerical answer right now. We can write it at the end if you find it comfortable, otherwise you can keep it as it is, because these values are numerical values and cosine is going to go up to, it will go on up to 4-5 decimal places, so don't write down decimal right now. Okay, so therefore f of a is p f of d p inverse when you do. So p is 1101, f of d is cos 1 0 cos 2, and p inverse is 1 minus 1 and 0. So on simplification, what do we get? We will get here cos 1, then we get 0, here it is 1 cos 1, and here it is cos 2. Matrix remains as it is, 1 minus 1 0 1, and finally we are having here as cos 1, then there is 0, and here it is cosine 1 minus cosine of 2, and finally here there is cosine of 2. So I have obtained therefore f of a. F of a is cos a, right? So this is cos of a equal to cos 1 0 cos 1 minus cos 2, and this is cos of 2. So this is the final answer. Okay, here the topic gets over. There are more things, but this much is more than enough right now for the detail of eigenvalues. So I stop myself over here. If you have any queries, anything, you can ask me. I would be very happy to help you on this topic. Chat sections and the comment sections are always open for everyone. Whoever has any doubt, you can let me know. I am extremely delighted that we are able to cater through this nice software. Live sessions are there and great, and so a lot of work is there. Yeah, thank you. You are clear with what we did and you are able to follow. There is nothing more. If you wish to have any practice questions, then you take up any random matrix. Don't take up random matrix, but take up a good question and see. All what you need to do, I'll tell you in short what can happen with a matrix. You can have in examinations in all across the globe. Okay, there are more shortcut techniques are there, but we won't bother about. We are talking about long lengthy answers. So A can be 2 cross 2 matrix in exam, or A can be a 3 cross 3 matrix. Okay, what all things are required. Now we are just giving a summary of what all things can happen with the matrix A. What all things can happen? First thing, A, they will ask what all questions they can ask. Find eigenvalues and eigenvector. This is the thing. Second, show or check whether matrix is diagonalizable. Okay, third thing they can ask you is they can ask you verify Cayley-Hamilton theorem. Okay, this is what they can ask. The fourth thing they can ask you in this is using Cayley-Hamilton theorem, using Cayley-Hamilton theorem, find A inverse or some expression they can ask you. Okay, expression value or term, something they can ask you like that. That is one kind. Show or check the matrix whether the matrix is diagonalizable, something like this can be asked. These are the kind of questions that generally come in the eigenvalue section. The next thing is that using a fifth one, they can ask you find uh, a raised to n or some powers, okay, powers or some function e raised to a or cos a, tan a, or tan 3a, something like this they can ask you, okay, something, some power or some function they can ask. The next thing what they can ask in exam is find the eigenvalues, find the eigenvalues of a, of a raised to 3, or like some find the eigenvalues using properties, okay, using properties, the one that we did today, properties, okay, properties of eigenvalues. So maybe some expression is there, a cube plus 3a square minus a inverse, find the eigenvalues, that kind of questions can come. There are few tricky questions are there. I'll hold one more session, maybe uh, next Sunday or something, where I can guide you on two tricky questions, two or three tricky questions are there in my mind that they can ask you. Generally they don't ask in a final exam, but let's give a try if they come, or maybe they're just purely intellectual based, but yeah, they are good tricky questions. No, students can they are mixture of all the 3 4 concepts, uh, because see, this topic which I gave you right now has maximum number of MCQs can be formulated. Now in your exams there are no MCQs, but maybe you can, if you are giving any competitive exams, or you are preparing for gate exam or something like that in future, or maybe you are still doing something, then maximum questions can be formulated, because there are so many tricks and so many loopholes are there to, to get the questions twisted, and many things can be formulated over here and can be asked to check and verify, and then you can uh, have multiple options also. So these are all on my side. If you want some questions for your practice, you can take same some small questions for your exercise on your own, so you can do all these questions. The first 4 can be done easily. For this you can try them, try like for a, I'll give you 2 1, so you have some simple questions coming ahead. So find the eigenvalues, eigenvector, yeah, you can try this. Yeah, this sounds good. 2 0 1 0 2 0 1 0 2. This looks a good question. You can even try this second one, as minus 2 2 minus 3 2 1 minus 6, then minus 1 minus 2 0. You can try this. Third, you can try um, um, you can find eigenvalue, find, for each you have to find eigenvalue and eigenvector and verify Cayley-Hamilton theorem. Okay, and sometimes it is use CHT. I generally don't use, but just for short form, uh, for this purpose, find eigenvalues for um, 234420003 for this, and for a equal to, and for a square minus 2a plus I. You can try this, and if you want more, you can max you can do here is find e raised to a. That's it on my side. Yeah, that's it on my side. um, I don't want to bother you on more of the questions on this. Okay, so please check all these things on your own. Let me know if you have any difficulties. We'll meet on next Sunday. Sunday morning we'll meet, and maybe some other time I'll give you the update. You can try, and yeah, that's all from my side, and let me know your difficulties. Okay, so that would be a doubt solving session, as well as those tricky questions that I have promised you. So that's all from my side. If you have anything, let me know. Yo, thank you, thank you, thank you, thank you. All clear from everyone, those who have attended, and thank you for being a great audience, a very interactive. It's my first time I tried this kind of. Is it possible to start complex integration? Dear, complex integration thing is already available on my YouTube channel. um, yeah, a complex, I have already delivered lectures. My video recordings are already there regarding how to do complex integration, the line integration, the Taylor series and Laurent series I have already explained there. And only thing is, what is missing out is Cauchy residue theorem and Cauchy integral formula. I will soon schedule something for that too. uh, okay, we will soon see for that also. Don't worry, stay geared up. I will surely take up those kind of questions also, or some videos, or maybe a live session will come on that too. It will be soon there. Okay, so don't worry, I have that in my mind, and we will complete it. Okay, so I will surely start on that too. So, and hope we get more number of people coming live and understanding the concepts and getting it done. So thank you for joining in. I'll close the stream. Have a great Sunday. Enjoy.